Welcome to Introduction to the EEG. In this lecture, we're going to go over a few basics of EEG. EEG basically measures electrical activity in the brain. So in order to really understand the EEG and how to process the EEG signal, we first have to understand the origin of the EEG signal, and that begins with some basics of electromagnetic fields. So in this lecture, we'll review electromagnetic field theory. The first thing to remember is the electric potential, and the best place to start is to remember that when we have two charges, Q1 and Q2, there's a force between them. The direction of the force is along the axis that connects the two charges, and the magnitude of the force is given by this equation, where Q1 and Q2 are the value of the two charges, and polarity here is included, so a negative charge would have a negative sign associated with it. Epsilon naught is a constant permittivity of free space. R is the distance between the two charges, and A hat is the unit vector that's directed from charge 1 to charge 2. So it then lends itself to talk about the electric field. So an electric field would be defined as a force per unit charge. The force per unit charge, if we just have a single charge, it's directed radially outward if the charge is positive, inward if the charge is negative. An electric field is always directed in the direction that a positive charge would move should it come into the field. And the field falls off. It's really the same equation as the force equation. You can see the equation here. Basically the only difference is instead of Q1, Q2 in the numerator, we just have a single charge Q. And in the denominator, notice that the electric field still falls off according to the inverse square law as 1 over r squared, with r being the distance in this case that you are away from the charge. So a couple of things to note. First of all, electric fields are vectors, and because they're vectors, they're also linear. They obey superposition. So if you had n different charges, you could basically find the electric field at a given point by summing up the individual electric field contributions of each individual charge. And so this is going to be an important fact, because what this means is if there are sources that are distributed in space, that the field is basically the superposition of the field due to each individual source. That'll have important repercussions in analyzing the EEG. So the next definition is the electric potential. And basically the easiest way to talk about the electric potential is to think about the electric field. The electric field is basically the spatial gradient of the electric potential. The electric potential is a scalar. The classic definition is if you took a unit charge located at infinity and moved it from infinity, where ideally the voltage or the electric potential is going to be defined as 0. So if we move that unit charge in from infinity to a given location within the electric field, that would be the electric potential, where the electric potential at infinity is defined as 0, or an ideal ground out at infinity. So we can basically compute the electric potential for a single charge, and we could do that by integrating the electric field, or we could compute the electric potential for a single charge based on Maxwell's equations, which we really aren't going to talk about at this point. Anyway, what we end up with is the electric potential at some point r is the equivalent of the value of the charge q over 4 pi epsilon naught r, where r is the distance away from which we are from the charge. So if we have a single charge in free space, it creates an electric potential, and that electric potential falls away according to the inverse law, or the 1 over r law, and it's a function of the value of the charge and the distance we are away from the charge. Now, like the electric field, the electric potential also obeys superposition. The only difference here is that we're not taking a vector sum. If we want to calculate the electric field due to a number of charges and we sum them all up, because electric field is a vector, we're having to take the vector sum. If we calculate the electric potential, then we just sum up all of the electric potentials for n different charges, and we end up with the electric potential due to the total charge. So for a single point charge, the field is radially directed, and there's something that we can define known as equipotential surfaces. Equipotential surfaces would be surfaces in 3 dimensions that, as a general rule, that all have the same potential. So if you have a point charge and the field is directed radially, the surfaces of equal potential end up being spheres with the point charge at the center. And that's pretty intuitive because obviously, we can go back and look at this slide, because the potential is a function of only the distance away from the charge. Clearly, there is a sphere formed of radius r, where anywhere on the sphere you're the same distance away from the charge, so obviously your potential would be the same. What's maybe not intuitively obvious, and this is the case not just for a single point charge, but for electromagnetic fields in general, the equipotential surfaces are always the surface that is defined as the surface that's perpendicular to the direction of the field lines. So clearly if the field lines are radial, then the electric potential, equipotential surfaces would be spherical. Now, what's going to be important in this class is not the field due to a single point charge, because we don't have isolated point charges in our brain. We actually are charge neutral in the brain. Because of the way brain cells are structured, what we tend to have are charge distributions that look like electric dipoles. So the electric dipole consists of 2 equal and opposite charges. So the top charge could be positive, the bottom charge could be negative, or vice versa. They're separated by a distance d. And then if we come out some distance, if we define the center point as this line indicated here, it's directly in the center of these 2 charges. If from that center point, which we'll define as the origin of our axis, we come out some value r, then based on the fact that electric potentials obey superposition, we could sum up the electric potentials due to each charge. And being that one is positive and one is negative, then we will have 1 over r1 minus 1 over r2, where r1 is the distance to the positive charge, r2 is the distance to the negative charge. And then if you make some assumptions, and the main assumption that you make is that you're much farther away from the charge, from the dipole, than the positive and negative charge are separated from each other. So in other words, you're pretty far away from this dipole. And if you do that, then you can make an approximation based on doing a little bit of trigonometry and putting everything in terms of little d and little r. And the cosine that go back to the figure, cosine of theta is the angle that little r makes with the z-axis. So if you do a little bit of trigonometry, you find that the potential can be expressed as a single expression that's a function of the value of the charges, the separation distance between them, the distance you are away from the charge, and the angle that you are away from the z-axis. And so if we now plot that, we get what is known as the dipole field. You can find this on a couple of places. On Wikipedia, there's a pretty nice figure. Also, throughout the semester, we will take advantage of the demonstrations at wolfram.com. You can see the electric dipole potential there, and that is interactive. So you can play around with the potentials and change charge values, change separation distances, etc. For most physical systems, the field can be expressed as a combination of point charges, including dipoles and higher order charge distributions like quadrupoles. And when we do that in field theory, that's known as multipolar expansion. The main difference between the ideal situation for electric fields and what we face in the brain is that despite what some of your high school teachers probably told you, your brain is not a vacuum. It actually does contain a number of different kinds of tissues. You have spinal fluid, you have your skull, your scalp, your hair. And as electric fields pass through these tissues, they are attenuated or changed in some way. Fortunately, the brain itself is a fairly poor conductor, so the losses are not huge like they would be if you were trying to propagate an electric field through a good conductor. And the skull, it actually passes electromagnetic fields relatively easily. So while that has to be taken into account in a model, it's certainly not a deal breaker for trying to model how electric fields, especially dipole fields, within the brain actually propagate to the surface of the brain so that they can be measured with the EEG. If it's been a little while since you've taken electromagnetic field theory and some of these concepts seem a little foreign to you, then there are a number of sites or textbooks or tutorials that you can look at just to review this idea of the most important ideas are that the dipole field is going to die away with 1 over r, which means we can't be too terribly far away from the source or we're not going to pick up the field. The other important concept is the fact that fields obey superposition. Both the potential and the electric field value itself obey superposition.